Okay, so now we are going to push this further, right? Now I'm going to generalize this. Let me arrange these P nodes in, let's say, D dimensions. And let me just straight away talk about a torus, right? I think by now it's clear that a torus is much more advantageous in comparison to a grid, right? A mesh. So let me straight away talk about a D-dimensional torus. So what's going to happen in a D-dimensional torus? Well, I'm not going to draw out a D-dimensional torus. Let me just make a 3-dimensional cube, right? And then you can kind of generalize. You have to think a little bit, right? Okay. So D-dimensional torus, so what are we assuming? So the dimensions are p to the power 1 by d times p to the power 1 by d times p to the power 1 by d and so on, right? D times. Yeah, that will give a total of p processors. Of course, in practice, you know, a 2D mesh doesn't mean that it has to be root b by root p. You have 10 cross 40 and so on. Each dimension can have varying number of nodes, right? But right now for theoretical analysis, we are just considering simple cases, right? Symmetric cases. Okay, good. Now this is going to be slightly more challenging, but still handleable. So let's start with degree. What is the degree here? How many links are connected to each node? So it's a torus, remember? So there are wraparound links also. So don't just go by this picture, right? Try to imagine it yourself. Try to generalize a 2D grid, right? So 2D grid had 2 dimensions. In each dimension, it had 2 links. Yeah? Is that clear? In each dimension, you have 2 links. One to the right, one to the left, one up, one down, right? 2D. Is that clear? That's the degree you're going to have, that every node is going to have. What's the total number of links? There's another way to analyze this. Each node has degree 2D, right? And there are p nodes, right? But we've counted every link twice. So the total number of links is pd. Yeah? Diameter? How many nodes in each dimension? P to the power 1 by d, right? So you have to go half the distance along each dimension. So p to the power 1 by d divided by 2, that's the distance you have to travel in each dimension, and you have to travel this distance in all the dimensions, times d, right? And finally, bisection width. This is a little more tricky, so you have to be careful about this. How am I going to divide this network? For that, let's look at this cube, right? How am I going to divide this into 2 halves? So this is one way of dividing it, right? You take a plane and you cut it right down the middle, right? Is it clear? It's a plane. In 2D, we used a line to cut down the middle. In 3D, we had to use a plane, right? So how many links are crossing this? So here is the important thing to note, that the links which are parallel to this plane will not cross the plane, right? Links across all other dimensions will cross the plane. So there are 3 dimensions here, yeah? One of the dimensions is not going to cross this plane, but along the other 2 dimensions, the links are going to cross this plane. Is that clear? So you will see something like this, right? One dimension, and then below this, green is one row, blue is another row, and so on, right? If I just take the projection on this green plane, right, what is that projection going to look like? You'll see 4 links crossing over here, right? It's going to be exactly a 2D grid. Okay, so what is the bisection width? Two p to the power 1 by d. You're only considering links of one dimension.
Into d minus 1.
Into. Should I explain this in 3D? What's happening in 3 dimensions? Do you understand what is happening in 3 dimensions? So let me first consider this, right? So in 3 dimensions, let's say you have p to the power 1 by 3 times p to the power 1 by 3 times p to the power 1 by 3, right? That's the arrangement you have. Somewhat like this cube, right? Now, you divide it into half, this plane over here, how many links will that contain? So here is what you have to understand. It contains p to the 1 by 3 times p to the power 1 by 3 links, which are crossing. Okay? One dimension is parallel to the plane, all the other dimensions are crossing. So one link for each of the other dimensions is going to cross this plane. You have to imagine this. I mean, there's no other way. You think of it like a cuboid. Let's say that you take a plane and you cut it across, let's say the length, right? Then the dimensions, the width and the height, those dimensions, there is one link for each of those which is going to cross. So width into height, that's actually the area of the plane that cuts.
p to the power d minus 1 by d.
P to the power d minus 1 by d. This is in 3 dimensions. So generalizing this, what happens in d dimensions, one of the dimensions is not going to cross, all the other dimensions are going to cross. So p 1 by d to the power, how many? D minus 1, right? D minus 1 dimensions are going to cross. Yeah? And actually there are 2 links crossing for each of these, right? So it's going to be 2 times this. Okay, so let's capture this and then let's have a quick look, right? So degree is 2D, number of links is roughly PD, diameter is d into p to the power 1 by d by 2, and what is the bisection width, right? 2p 1 by d minus 1. Yeah, so I can write it as 2p d minus 1 by d or 1 minus 1 by d, whatever. Yeah. Okay, compare it to the other networks, right? Now the number of links you have to make a trade-off somewhere. The number of links is still a factor p, right? So you can choose your p. You want to go 4 dimensions, 5 dimensions, it's really up to you. So 5D torus people have built, right? Degree not too bad, 2 times d, handleable, right? Even if you have a 5D torus, you just have 10 links going out, not too bad. Diameter, not too bad. Yeah, p to the power 1 by d is quite small, okay? And bisection width is also very good, almost linear. Yeah, which means very good communication, okay? D-dimensional torus. So that's why people have explored these to quite an extent, right? D-dimensional tori. All right.